Hey guys, welcome to chapter 5. So in chapter 5, we're going to continue talking about chemical bonds, but we're going to talk more in this chapter about covalent bonds. So just to remind ourselves what we've talked about up until now, we focused all of our attention, or most of our attention in chapter 4 on ionic bonds. So ionic is a metal bound to a nonmetal. And when a metal and a nonmetal come together, they typically exchange electrons. So somebody gives one away, somebody takes an electron, and that forms our ions, right? Our charged particles. What we're going to dive into now is covalent bonding. So in covalent bonding, we've got a nonmetal bound to another nonmetal, and electrons are shared. Electrons are shared in this case. So the way that we are going to look at these covalent bonds and how they happen and how they share electrons is we're going to talk about Lewis structures. So Lewis structures are going to be the position that we take to help us to understand these covalently bound molecules. So Lewis structures, no surprise at all, focus on valence electrons. These are sometimes called electron dot structures. So what we do is we draw electrons as dots around these structures. So looking at the Lewis structure for just an atom of oxygen, what we're going to do here is we're going to draw the symbol in the middle, and then you can think of an imaginary box around the symbol. And on each side of that imaginary box, we're going to put up to 2 electrons. So for oxygen, we know oxygen has 6 valence electrons. So we would write 6 dots. 1, 2, 3, 4, 5, and 6. So again, up to 2 dots go on each side of that imaginary box. I don't really care if you pair the dots up like I did. So 2, 2, 2. Or if you pair, and put one here and one on that side, it doesn't really matter to me. As long as there's 6 dots around that chemical symbol, that's really what I'm looking for here. Okay. So let's try a couple. So go ahead and pull out a periodic table if you don't already have one out. Pause the video and see if you can do the Lewis dot structure for an atom of argon and a Lewis dot structure for beryllium. All right, for argon, we're going to draw the chemical symbol for argon, which is just simply AR. Argon is in the 8th row or 18th column, so it has 8 valence electrons. So I'm going to draw 8 dots around it. 1, 2, 3, 4, 5, 6, 7, 8. So that's the Lewis structure for an atom of argon. Switch colors. Beryllium. So the chemical symbol for beryllium is Be. Beryllium is in 2A, or the second column. It's going to have 2 valence electrons. In this case, it does not matter where you put those 2 dots, just that you have 2 dots around it. So you could do 1, 2 if you wanted. Really, they could go anywhere around that atom. But as long as there's 2 dots, that's what I'm looking for. So here is the Lewis structure for beryllium. Couple rules that we need to talk about before we dive into a Lewis structure of a compound, so putting atoms together. So notice that this is the Lewis structure for neon. Neon is one of our noble gases, right? And our noble gases, we know, are particularly stable, right? So we've seen this before. We're going to continue to see it again. There's something magical about the number 8 when it comes to chemistry. So all of these atoms are going to share electrons in order to have what's called an octet. So an octet is having 8 electrons in the valence shell, and that's what makes them particularly stable. So the whole purpose of this sharing exercise, this chapter, is going to be to have an octet. Now, there are a couple exceptions to this octet rule, but they're pretty easy to understand. So our big exception to the octet rule is what's called a duet. So a duet is having 2 electrons in a valence shell, particularly in the first valence shell, and that makes it particularly stable. So if you look at your periodic table, you'll notice that helium is above the noble gases in row 18 or 8A. Now, does helium have 8 electrons in its valence shell? No, helium only has 2 electrons total. But having 2 electrons in that first energy level does make it particularly stable. So helium has a duet, and he's happy with a duet. All of the atoms around helium, the ones that strive to be like helium, are also going to be okay with a duet. And the one that we will focus on, the one that you really will need to remember, is this guy right here. So hydrogen. When hydrogen shares electrons, he's going to be happy just sharing 2 electrons because a duet is going to satisfy him. So that's the one exception to the rule that we need to talk about before moving forward. But like I said, it's pretty easy to understand. Okay. So the best way to do these Lewis dot structures is just to really dive in head first. I'm going to go through a series of steps, and in a couple slides, I have these steps written out for you. What I want you guys to do is really just kind of sit back and watch and listen right now. So we're going to do the Lewis dot structure for water. So water is H2O. So the first thing we need to convince ourselves is that this is, in fact, a covalent bond. So hydrogen is a nonmetal. Oxygen is a nonmetal. So nonmetal bound to a nonmetal, that's covalent bonding. We know they're going to share. Okay. So the first step is to determine how many valence electrons we have at our disposal. How many valence electrons do we have to share and shift around in order to make everybody happy, to have an octet or a duet? So hydrogen, each hydrogen atom has 1 valence electron that it's going to bring to the party. I see this subscript of 2 right here. So I know I have 2 atoms of hydrogen. So each one of those guys brings 1 valence electron. And then oxygen, looking at the periodic table, he's in 16 or 6A. So oxygen is going to bring 6 valence electrons to the party. So we add these all together, and we've got 8 valence electrons at the party, or 8 valence electrons at our disposal. The second step is going to be to draw some sort of skeletal structure. This is going to get easier the more that you practice it. But in chemistry, think symmetry. Chemistry is very symmetrical. So I have 1 atom of oxygen, 2 atoms of hydrogen. So I'm going to have my oxygen in the middle and my hydrogens on either side. Okay. So think a symmetrical approach here. All right. So after I have kind of my skeletal structure on the paper, and this would be step 3, I'm going to start distributing or giving electrons away until I've used all 8 valence electrons. I always start with the electrons that are shared between atoms. So these two electrons are being shared by both the hydrogen and the oxygen. So I'll put 2 in there. And then I'm going to put 2 more electrons over here because oxygen's sharing those 2 electrons with this guy. Okay. So I put 1, 2, 3, 4 electrons onto the paper. I have a total of 8 electrons that I have to use. So where are the other electrons going to go? Well, oxygen still needs some, right? He wants a total of 8. Right now he only has 4. So I'm going to put 2 on the top of his imaginary box and 2 more on the bottom of his imaginary box. Okay. All right. So the first thing I'm going to do to check my answer is to make sure that I've used all of the electrons that were brought to the party. So I have to use 8. I cannot use more because they wouldn't be available. I cannot use less because they're there. I have to use exactly 8. So let me count how many valence electrons I put into this structure. So 1, 2, 3, 4, 5, 6, 7, 8. So that's the first check. I've used 8 electrons and 8 electrons were brought to the party. So that's done. The next thing we need to check is that everybody's happy, that everybody is satisfied with the number of electrons they're sharing. So how many electrons does hydrogen want? Yeah, hydrogen's one of those exceptions. So hydrogen's okay with 2. So this guy right here, how many electrons is he touching or how many is he sharing? He's touching 1, 2 electrons. So he's happy with that duet. And yes, I draw smiley faces on my atoms. It's just what I do. All right, let's go to this hydrogen over here. So this hydrogen, how many electrons would make him happy? What is he satisfied with? Yep, he's satisfied with 2. So 1, 2 electrons that he's touching. So he is happy. He's got his duet. All right, so let's go to our oxygen here. So how many electrons does oxygen need to satisfy him? How many electrons does he want to touch? He wants to touch 8. So let's count them. So oxygen is touching 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's octet is satisfied or whole, and he's happy. So this is the Lewis structure for water. Calculate the total number of electrons that are brought to the party. Draw the skeletal structure, then distribute the electrons to try to fill as many octets. Okay. Before I go through that step-by-step process and we do some more examples, I want to just get some terminology out of the way. So here's our Lewis structure for water. We see 2 different types of electron pairs. So that's probably the first thing we need to talk about. When we talk about covalent bonding, we typically talk about electrons and pairs. They like to run around in groups of 2. The first type of pair that we're going to talk about is a bonding pair. So a bonding pair is going to be the electrons that are being shared between 2 atoms. So these electrons between the oxygen and hydrogen, and these electrons between the oxygen and hydrogen. So this Lewis structure has 2 bonding pairs. Now the electrons that only belong to 1 atom are called lone pairs. So in this case, the oxygen owns 2 lone pairs. He owns them all alone or by himself. So the lone pairs on this oxygen atom are right here on the top. That's 1 lone pair. And down here on the bottom, that's another lone pair. Being able to quickly identify bonding pairs and lone pairs is going to be really important in the coming videos because we're going to start talking about shapes. And the number of lone pairs and bonding pairs helps to dictate these different types of shapes. Okay, so the other thing I want to talk about is this. So bonding pairs are often drawn or depicted as lines. So you're going to get sick of drawing dots. It's going to happen. And when you start putting these into different programs like Pearson or Chem 101, you're going to start to see bonding pairs drawn as lines. The big take home here is that each line represents 2 electrons. So when I'm counting total number of electrons here, I would count 1, 2, and then when I come to a line, I would count 3, 4, because it represents 2 electrons. So that's the only other thing I wanted to talk about on this slide was the fact that bonding pairs are often depicted as lines. Okay. So let's do some examples. So go ahead and pause the video and see if you can get the Lewis structure for CH4 for methane. All right, so first step here is to calculate the total number of valence electrons brought to the party. So carbon is going to bring 4 valence electrons to the party. Each atom of hydrogen is going to bring 1 valence electron. And I see that there's 4 of them. So you could draw out 4 hydrogens. Or what I often do, because I'm a lazy chemist, is I just multiply that by 4. And so I have a total of 8 valence electrons. All right, step 2 is to draw the skeletal structure. So I've got 1 carbon, I have 4 hydrogens. So likely each of those hydrogens are going to go around the carbon. So 1, 2, 3, and 4. Okay. And then step 3, once I have this skeletal structure on the paper, I'm going to start distributing electrons, filling as many octets as possible, and remembering to use all of the electrons at my disposal. So I like to start with bonding pairs. I like to start with the electrons that are shared between 2 atoms. So I'm going to start with 1, 2, 3, 4, 5, 6, 7, 8. So I've used all 8 electrons at my disposal. Now I need to go back and just make sure that everybody's happy. So hydrogen, what is hydrogen happy with? Yep, he's happy with a duet. So he's got 1, 2, this guy 1, 2, this guy 1, 2, this guy 1, 2. So all the hydrogens are touching 2 electrons. What about carbon? So carbon wants an octet. He wants to touch 8 electrons. So if we look at carbon in the middle, he's got 1, 2, 3, 4, 5, 6, 7, 8. So he's got his octet. He is happy. So this is the Lewis structure for methane. Your total number of valence electrons is not always going to be 8. That just happens to be some of the simplest examples. So those are the types of examples that we start with. So here you see the dots. So if you prefer to draw dots, that is perfectly acceptable. So here our bonding pair depicted as dots, and here our bonding pairs are depicted as lines. Okay. See if you can try this one. So go ahead and pause the video and see if you can get the Lewis structure for ammonia. All right. So step 1, how many valence electrons are at our party? So nitrogen is going to bring 5. Hydrogen's going to bring 1 valence electron, and there's 3 of them. So 1 times 3 is 3. And then we add those up. We've got 8 valence electrons at our party. Okay. Skeletal structure. So nitrogen in the middle and hydrogens around. Again, even though we're drawing atoms around it instead of dots. We still like to stick with our imaginary box. So a hydrogen goes on each side of the imaginary box here. All right, so that's our skeletal structure. And now we're going to start distributing electrons to fill as many octets as possible. So again, I like to start with bonding pairs. So 1, 2, 3, 4, 5, 6. So I have 6 electrons on the paper. I have 8 that I need to find a home for. Where do you think the last 2 electrons might go? Yeah, they go on top of the nitrogen as a lone pair. So we're going to put them up here on the top. So to check my work, I want to make sure that I put 8 valence electrons on the paper. So 1, 2, 3, 4, 5, 6, 7, 8. So I've used all 8 electrons that were brought to the party. Now I got to make sure everybody's happy. So hydrogen is happy with his duet. 1, 2. Hydrogen is happy with his duet. 1, 2. Hydrogen's happy with his duet. 1, 2. Nitrogen. All right. So nitrogen wants an octet. Nitrogen wants 8. So he's got 1, 2, 3, 4, 5, 6, 7, 8. So he is happy, and this checks out as the Lewis structure for ammonia. All right, so here are those steps written out. Underneath each of the steps is some helpful hints. Some of the helpful hints we're not quite ready for, so we'll get to that eventually. The ones that we're not ready for, I'm just going to kind of skip over. So step 1 is calculate the total number of valence electrons. One of the biggest mistakes that students make is they try to say, oh, nitrogen brought 5 valence electrons. It must make 3 bonds. Well, that works for very simple structures, but as things get more complex, that completely crumbles and falls apart. So when you calculate the total number of valence electrons, picture it like this. So let's say that you're going to a party and you're bringing your own beverages. We'll say soda, for example. So you get to the party and the host is like, go ahead and just throw your soda over here in the cooler. Just remember how many you brought. So you take your soda, you dump it in the cooler, and you start hanging out. You brought with you 4 sodas, right? So you go in there, you grab a soda, you open it up, you drink it. Doesn't really matter who brought that soda to the party. What matters is you got to drink that soda. So you're ready for another one. You reach in the cooler, you grab it, you open it, you drink it, okay? Electrons work very much the same way. Once they bring their electrons to the party, they don't really care who drinks the soda. They don't really care who gets the electron, as long as everybody's happy at the end. All right, so step 2 is draw the skeletal structure. So here we're again thinking symmetrical. So try a symmetrical approach first. So if there's 2 hydrogens, 1 oxygen, probably the 2 hydrogens are going to be around the oxygen. And then hydrogen will always be terminal. What do we mean by terminal? You'll never find hydrogen in the middle. So let's say we've got H2O, right? You'll never see something like this, where hydrogen's in the middle. Why not? Well, hydrogen wants a duet. And if hydrogen's in the middle, how many electrons does this hydrogen in the middle have? He has 1, 2, 3, 4. Yeah, that's never going to happen. So you will always see hydrogens as terminal or on the outside here. Okay. So symmetry, hydrogens are terminal. Step 3, distribute electrons, filling as many octets as possible. So down here, we've got a little helpful hint. We'll get to that as we get more proficient. Once we start doing some more structures together, then I'll come back to this helpful hint. It works amazing for some people. and it absolutely blows other people's minds and they hate it. So we'll come back to that. If it works, great. If it doesn't, no big deal. But distribute electrons, filling as many octets as possible. Again, just from experience, I like to start with bonding pairs first and then go back and do lone pairs. But the more you practice, the more you'll find your path. And there is a step for, so if an atom lacks an octet, explore double and triple bonds. We haven't gotten to those examples just yet, so we'll get to those in the next video. But I went ahead and put them in the steps here because we'll get to them very shortly. So this is your introduction to Lewis structures. In the next video, we're going to get a little bit more complex, talk about a couple of the helpful hints in here, and just keep building on this skill. I hope you found this helpful.